welcome to the last part of the stream for first semester AP Calculus stuff. So, in the past ones we talked, basically this morning I decided, oh, I'm gonna stream for my class, why not just make it something for anyone that's taking the class. So this is for Calc AP and Calc BC both, and the last things that we covered were pretty much everything except for what's going to be covered right now, which is applications of integrals, which essentially is going to be bounded areas, disks and washers, cylindrical shells, and then kinematics. So kinematics basically is just the physics stuff in calculus. Then differential equations, we're going to go over some of that. And Euler's method is at the end, and I kind of forgot to go over mean value theorem in the other video, so I'm just going to quickly improv that here. Alright, let's get started. So, bounded areas. The general idea here is to try to find the area that is in between the curves. So we can kind of think about it as, here's the area that's under the top curve, and then here's the area of the bottom curve. So if we get rid of the area of, so essentially if we take the area of the top and subtract out the area of the bottom, then we end up with this. We end up with the actual bounded area that we want. So essentially the area is the integral from a to b of the top curve dx minus the bottom curve dx. In other words, in terms of this, you can say the integral from a to b of, you don't have to use two different integrals, you can just do that in one, because linear, it all works together, right? So in this case, the top curve is g of x, or at least within that, and then the bottom curve is f of x dx. Alright, so what about things like this? Well, similar thing, except you can do two things. You can either do the integral from a to b of, let's just call this f of x and this one g of x, and do integral from a to c of f of x dx plus the integral from c to b of g of x dx. So that works, but another way that also works if you want to write in one integral is, let's just say that, yeah, that's f of c. Let's just call that capital B, because why not? Integral from 0 to b of, so remember when we integrate toward the axis, right? So the area between the curve and the axis. Y-axis is this way, so we're going to look like this. So up there we had this whole thing, so we're like looking downward minus the other downward equals this thing. Here we can do the rightmost curve then minus the leftmost curve. Rightmost curve is, if we write this in terms of y, it'll be f of y. If we write this in terms of y, that'll be g of y all dy. So essentially what'll happen, let's just say, okay, what could this be? This could actually be, let's just say this is y equals square root of x, that looks like square root of x, and y equals x minus 4. Let's just do that. So if we were to actually do this out as a dy thing, then we can isolate for x, and then we get x equals y squared, and x equals, wait, that should be 4 minus x, sorry. 4 minus y. Where do they intersect? Y squared equals 4 minus y squared plus y minus 4 equals 0. Hopefully this is not a weird integral. Let's make that a 6. So that'd be y plus 3 times y minus 2 equals 0. Okay, so y equals 2 is going to be the one we're interested in. So 0 to 2. So the right curve is going to be the line 6 minus x, 6 minus y, minus left curve, which is y squared, dy. So this becomes a fairly easy integral. We get 6y minus y squared over 2 minus y cubed over 3 from 0 to 2. I'm going to erase this work just so that we have space. And then we end up with 6 times 2 is 12 minus, say 2 times 2 over 2 is just 2 minus 8 over 3. Which equals 10 minus 8 thirds, which is 30 minus 8 is 22 over 3. Alright, so that's what we're going to get if we were to do this as a dy integral. Dx integrals are generally really easy. You just find the points of intersection and just like do that. You don't have to change things between x's and y's or whatever. That's why I only did an example of this. Generally, everyone's able to kind of do the other ones. Okay. So then, let's get started with volumes. And we're also going to get into this with volume anyway. So actually, what I meant over here was, I want to make it basically that thing up there, so I'm going to make that 5 minus x instead of x minus 5. So I'm just going to change that real fast. Oh, cool, I'll have to change it there. I hope this works as I think it's going to work. Oh well, let's see. So let R be the area in the first quadrant bounded by these two curves. So let's draw that. This is going to be square root function shifted to the right by 1 unit. And this is going to be a line with -1 slope. Intersects at 5 and 5, so there we get that. And we're going to rotate this around the x-axis. So we're going to get something that looks like this. So we get this like top looking thing, but just like shifted, rotated over on its side. So let's look at that. These are discs, right? Each of these little cross sections, you're integrating these, you're adding them. So remember, integration is just fancy addition, like really, really fancy addition. So you're going to add the areas of these things. Area of a circle is pi r squared, right? But they're not the same length. The r depends on something. And in this case, we actually need two integrals. So we're going to do integral from 0 to wherever they intersect. And let's see, what's this going to look like? From 0 to wherever they intersect, and then from where they intersect to 5. Because what we can see fairly easily is that each radius is just the distance between the x-axis and that function. So let's find what that point of intersection is. X minus 1. Square root of x minus 1 equals 5 minus x. If we square the whole thing, we get x minus 1 equals 25 minus 10x plus x squared. Hopefully this doesn't turn out too bizarre. Minus 11x plus 26 equals 0. Oh, we're going to have to use the quadratic formula. Negative b, so 11 plus or minus the square root of b squared, so 121 minus 4 times 26 is, okay, 4 times 25 plus 4. 104 all divided by 2. Okay, I'm just gonna call that K. So whatever the positive one's gonna be, so 11 plus the square root of that is just gonna be what this is. So we're gonna go from 0 to K of the first function plus the integral from K to 5 of the second function dx. Okay, so because this is not an integration video, I'd rather not go over the whole thing, but I'll leave the solution in the description. So there's just going to be like a whole list of solutions in there. So if you need to, just look in there. So complete this on your own and then go there. A lot of the time anyway on like the AP test and stuff, you'll be asked mostly to set up but not evaluate. So if it's something disgusting like this, chances are you're probably not going to evaluate, because here's the limit of integration. They just want you to set that up and call that K or like whatever. So in the interest of time, let's move on to the next one. Volumes by washers. So let's use the same R. So same picture, same idea there. Something like that. Actually, this is more accurate. And then we're going to rotate it around the y-axis. Okay, so let's actually redraw this so that it's easier to see how that looks. So if that's rotated around the y-axis, then we're going to get something like this. So it's going to be like this thing that just like rotates. I guess it's kind of like a bundt cake. But anyway, we have washers stacking upward, right? So a washer, that means you have a thing like this. What's the area of a washer? So you have an outer radius and you got an inner radius. So if you take the area of the outside minus the area of the inside, you get this. So the area of the outside is pi big R squared. The area of the inside is small r squared, pi small r squared, right? In other words, pi times big R squared minus small r squared. So the integral, so it's going to be the integral from 0 to, in this case, it's going to be 0 to whatever that height is where they intersect there. And then big R squared minus small r squared dy. Okay, so let's figure out what those things actually are. So since we're doing a dy, let's write this in y form. So we get y squared equals, okay, y equals square root of x minus 1. So if we square that whole thing, we're going to get y squared equals x minus 1. So in other words, x equals y squared plus 1. And here, the x and the y will essentially just switch 5 minus y. Alright, so we got that. So where are they equal in the y's? So set those equal. Y squared plus 1 equals 5 minus y. So we get y squared minus y plus y minus 4 equals 0. I think you might need a quadratic formula this thing. Yeah. Negative 1 plus or minus square root of 17 over 2. It's going to be the positive one. So we're gonna add. So -1 plus square root of 17 over 2. I'm just gonna call that k again. Again, just for simplicity's sake. And I will leave the solution in the description, so look for that if you want it. Whoops, there was supposed to be pi there. Pi r squared, so yeah. Okay. Big R. Let's think about what that is. So if our cross sections are these, let's try to make this look a little bit nicer. So each cross section, I'll use a different color. Is going to have a radius of this. And this. So the big radius, in this case, looks like it's just going to be the curve, the big curve, so the square root curve, minus 0, and then the smaller radius is going to be the line minus 0. All right, simple enough. So we get, let's see, where is it? There it is. So x equals that. So y squared 1, quantity squared, minus 5 minus y, quantity squared, dy. So this thing is the whole r squared minus big R squared minus small r squared thing. So we got that. Again, I'll leave the solution in the description, so do that if you want to. And then this is what it's set up as. If you get some kind of nasty like this, you're probably just going to have to set it up without actually evaluating it. Alright, very last one, cylindrical shells. So we're actually going to do the same problem, except with cylindrical shells. So let's do this. So draw it again, and then we're going to do another little thing with it. So this is what the shape looks like. So if we were to take a cylindrical shell, so take this little blue thing, and take a bunch of these and actually expand them outward. So this is actually going to be a dx integral. So it's going to be from wherever this is until wherever that is. So because we know what the function is, the first function is square root of x minus 1. That's going to start at 1. Then it's going to end at, so the second curve is 5 minus x. That's when x equals 5. So from 1 to 5 of... Okay, so now let's figure out what this is. We only want the outer shell, right? Just that part. We don't want the inside. We just want the surface area minus top and bottom. So if we look at it as there's a height, and then there's this thing, well, we can unravel this basically. And then there's a height, and then a base. The base is actually the distance around a circle, so 2 pi whatever r is. Okay, so the height. What is the height? So the height is the distance between here and there. That's actually the function value. The height is the function value. So that's f of x. And then the radius is the distance between the origin and this point. So that's actually just your x value. So for cylindrical shells, all you really need is volume equals 2 pi times x f of x. X times the function. So in this case, we have 2 integrals that we need. So remember that value k that I said earlier, that like weird square root thing? Yeah, that's going to be that. Because, okay, redrawing this. We're going to get some cylindrical shells from here. And then cylindrical shells from here. So I'm going to do this one as x times f of x. That f of x is going to be the square root of x minus 1 dx plus, and then from k to 5 of the next one, which is x minus 5 dx. Again, I'll leave solutions in the description later on. For here, just set it up, and yeah. So this is how this is set up. I know the cylindrical shells tend to be one of those weird ones. If you're able to visualize these, it makes it significantly easier. So try drawing things. Draw a lot. Get really good at drawing, and that'll help significantly with having you be able to do these types of problems with, well, with any method really. Okay, so next thing we're going to do is kinematics. So we're going to do some physics here and just like talk about it. All right, so position and displacement. Position slash displacement, this just talks about the distance between start and end points. Like a particle is traveling somewhere. Let's just say here's the particle. It's going a certain way, it ends up like here. Position or displacement represents this distance of the dotted line there. Versus if we're talking about distance, that would be how long this red length is. So can you see the difference between that? Distance is the whole thing. Position is just part of it. It's just, well, it could be the whole thing. Position is just where you start, where you end. Find the shortest distance between those. That's displacement or position. Usually it's denoted with x of t or s of t. I'm just going to use s of t for these for simplicity's sake. And so for those of you who are, chances are in BC, maybe AB depending on what your teacher did. So integration, if you're familiar with integrals, this is the definition of these two.